Assalamu alaikum dear students. We are now starting first lecture for week number 5 of our course of communication systems. In our last lecture we talked about AM modulation and its different variants. We have previously discussed the time domain representation of the AM signal as well as how the signal appears in the frequency domain. We have also talked about different variants of AM modulation, including double sideband and single sideband modulations. In today's lecture, we'll be talking about different modulators and transmitters that we use to generate AM, NDSB, and SSB signals. So primarily in today's lecture, we'll be talking about circuits that are used to generate amplitude modulation and its variants. So because we'll be dealing with circuits and their waveforms, so I thought it will be more convenient to go through directly the textbook rather than having a separate presentation on that. So I have taken the lecture notes from the textbook directly. So this one is actually section 4.3 from our textbook, that is Bruce Carlson. So we'll be starting this section 4.3 here, which talks about the modulators and transmitters in communication in AM modulation. So first of all, we start our discussion related to the AM modulation. Previously we have talked about the LTI systems, and if you recall, I mentioned that in LTI systems, whenever a signal passes through a linear system, there is a change in phase and there is a change in frequency. So frequency gets changed, phase gets changed, but I mentioned it wrong. Amplitude gets changed and phase gets changed. Whenever a signal passes through a linear system, amplitude and phase gets changed, but frequency does not change. So it's a basic property of any linear system that we always need to have. We will always get the same frequency at the output with different amplitude and different phase. However, when we look at the amplitude modulated signal, if you recall the frequency spectrum of the modulated signal, we notice that there are few frequencies which are not available in the original signal. Like if a signal has a carrier frequency which is represented by Fc and a modulating signal which is represented as a frequency Fa, in that case the output would contain three frequencies: Fc, Fc plus Fa, Fc minus Fa. In other words, the output would contain three components, namely carrier, upper sideband and the lower sideband. So basic thing that we notice is that there are generally new frequencies which we get at the output side whenever we modulate through AM modulator. So from this we can notice that the AM modulator is actually a non-linear system. It's not a linear system because it produces some new frequency components which are not available in the original signal. So one first thing that to note is that it's a non-linear system. The question is, how can we generate the AM signal? So in order to understand the basic production of AM signal or basic circuitry of AM signal, we should revert our attention to the basic form of the AM modulated signal, which is represented by this expression: xct is equal to AC cos omega ct plus mu xt AC cos omega ct. This is the basic representation of AM signal. If you notice that basically we are interested in getting two operations. What are those two operations? First one is represented by this term here. You can see that xt represents the message signal, and cos omega ct represents the carrier wave. AC and mu, they are constant, so for the time being we can just ignore them because they are only represented as the constant multiples. So main time varying component that we see in our waveform, they are actually appearing in form of a product or multiplication. So basic component of the AM modulator is the product of the message signal and the carrier wave. And second operation that we need to use is this addition. That means the addition of this carrier component to this product term. So if I ask you to plot a block diagram for the AM modulator, so this will look somewhat like this. You can see that we have this mu xt, which is representing the message signal with the weight of that modulation index. We need to multiply it with a multiplier, so we need to have a specific multiplier which should be present here. A carrier wave need to be generated, sorry, is omega m is wrongly mentioned here, it should be omega c because it's representing the carrier wave. So AC cos omega ct is basically generated by using a specific oscillator. So because as we know that there are certain circuits which are named as oscillators, so we can use oscillators to represent to generate this carrier wave. So as the carrier wave generates the oscillator, we will multiply this carrier wave with the message signal by using this multiplier, and after we get the multiplication, the result, the product of that multiplication operation is then added to the carrier wave again in order to get the overall AM signal. So this is the overall flow of the AM signal. So primarily if you look at this situation, so we will be needing three major components in the signal. First is this oscillator, which actually generates the carrier wave. So first thing for any AM modulator is the oscillator, which is represented by this thing. So we will use an oscillator to generate a carrier wave, and then we would be needing an addition operator, which is typically obtained by using operational amplifier. So this is the circuit of operational amplifier in addition configuration. So you can see that this op amp would be actually adding this signal which is coming out of this product and this cos omega t. So this operational amplifier performs the function of the addition here, whereas we need additional circuitry to perform this multiplication, which is represented by this block here. You can see that this block with a cross sign is actually used to represent that there is a circuit which is used for multiplication. So summary is the carrier wave is generated by an oscillator. This addition operation is generally achieved by this operational amplifier, whereas this multiplication is actually generated by a variety of different signals. So we need some hardware to generate this multiplication. So one of the possible circuit to generate this product term, this block of multiplication, is actually in electronics terminology it is named as variable transconductance amplifier. The variable transconductance amplifier is actually a variable gain amplifier. You can see it here. So actually it uses two transistors. You can see one transistor is here and one transistor is here. The output is obtained as a differential form. You can see that the output is actually differential of these two sides. So the output is given here. The gain is actually represented by this current of the emitter. So the this current which is coming out of this emitter, it is actually controlled by the circuit V2. So actually you should notice that for multiplication we are talking about two different voltage waveforms. One is xt, which is representing the message signal, and second is the carrier wave, which is representing the carrier which is representing the carrier wave. So message and carrier wave, they are two different voltage waveforms. So here you can see that one of the waveform is used as the input on to the base of one of the transistors, and the second voltage, say for example the message signal or the carrier, one of them is used to control the current here. So actually the property of this variable transconductance amplifier is that the gain is actually proportional to this current which is flowing through this emitter. So by using this voltage V2, we actually control the gain, and eventually the gain becomes dependent on this V2. So the whatever output you see here, whatever output you see at this differential side, it becomes dependent on the voltage multiplied by the variable gain, which is actually proportional to the voltage V2. So the output voltage becomes proportional to the product of V1 and V2. So this entire circuitry which is represented here is actually represented, it actually performs the operation of this multiplication. So basically this block here in this B diagram previously, this multiplication block, so one of the physical realization of this multiplication is this variable transconductance amplifier, which is illustrated here. So we have description, entire description onto that, but this is not the only interpretation of implementation of that multiplication. In electronic systems there are other possibilities of having different other sort of implementations as well. For example, there is a possibility of using logarithm and anti-log base amplifier. So what we do, the two signals which are illustrated here, xt, and second signal is our carrier wave, which is AC omega ct. So first we take log of these two by using one of the op-amp configuration is actually based on the logarithmic output. So we can set it to get an logarithm of these signals. So once we get the logarithm, then we pass it through an adder like this one. So we can pass it through adder, and then we perform an anti-log operation here. So we know that in logarithm, if two signals are added, so if we take the anti-log of that, so that will become multiplication. So it is a standard property of logarithm that if two numbers or signals, they are being multiplied, so in logarithmic form they will be added. So this is another possible implementation of this multiplication by using log and anti-log circuits. So first we take the log of both the signals, that is the message signal and the carrier wave, and then we add them together, and then we get the anti-log of that. So eventually you would get the product of both signals at the output side. Okay, so this is the overall illustration how we can generate AM signal by using a physical hardware. One of the important possibility or one of the important variant of AM is this DSB modulation. And if you recall, DSB is actually a variant of AM in which we only need product of the message and the carrier. So if we want to generate DSB signal and we do not need to have the entire AM output, so we would be needing this term at the output, which is xt, AC cos omega ct. So basic operation for DSB is actually the product or multiplication of these two signals. So if in any case we need to have this DSB at the output, in that case what we need to use this same circuit again, but the output will be get at this point only. Sorry. So output will be achieved at this point only, where you have the product of the signals only, the product only, and we do not need this op-amp part. This op-amp part would not be required because we do not need the multiplication, oh sorry, addition. The addition of that carrier wave is not required at that side. So eventually if we are talking about that signal, that part of DSB generation, so for DSB generation we only need to use this product term. So product can be achieved by using this variable transconductance amplifier, or there is another possibility of generating this product by using this log and anti-log circuitry as I discussed. So DSB and this AM signals, they are actually generated in they can be generated in same fashion because the primary difference between these two forms is actually addition of this carrier term only, and if we do not add this carrier term, eventually you will end up with the DSB signal. So you can see that we can use this type of circuit to generate AM signal as well as the DSB signals that can be used for AM transmission. One of the important thing that I should mention here is that this circuit which I have discussed, the product circuit that is based on the variable transconductance amplifier, or the product circuit which is based on the logarithm or anti-log amplifiers, in that case those amplifiers, they only work at low power levels and relatively low frequencies. So they are actually low level modulators generally, so they can be used in the applications where the power levels are relatively low. In case we need to use amplifiers at higher power level or higher frequencies, in that case these variable transconductance amplifier and log and anti-log amplifier, they become saturated and they do not provide the desired response. So for those purposes we need to use different modulators. So for different modulators, one of the important modulator is actually named as square law modulator. Square law modulator, as the name says, is based on the squaring of a signal, it is a very logical interpretation. As I previously said, the modulators, they are actually non-linear systems. So square law is also a type of non-linear system. It can be used to get AM signal at relatively high frequencies. So how do we achieve that AM signal at high frequency? So let me quickly discuss that thing. So let me first show you the square law modulator circuit. This is the square law modulator. So actually this is based on a non-linear element. So there is a non-linear circuit in which the input output, they are not directly related. Actually they are related with the square law. So this non-linear element is actually the main component of this square law modulator, where the input output relationship of that non-linear modulator is given by this mathematical expression. The output is actually dependent on square of the input. V in square, A2 is some constant number, V in A1 is also some constant, which is actually dependent on the values of this resistance and capacitance. And okay, so So this is the square law element which is illustrated here. So how do we perform the modulation using this square law operation? So first step towards having the modulation of the signal is to get the addition of this message signal and the carrier wave. Again, the carrier wave would be generated by an oscillator. So we would have an oscillator tuned at the carrier frequency which will be generating this carrier wave, and we will be having a message signal, and we pass it through an adder which can be implemented by using this op-amp, as I discussed before, that this op-amp actually performs the operation of addition. So we pass it through an adder to get the addition of this signal. So this input voltage V in, this will be actually equal to xt plus cos omega ct. So this will be actually sum of the message signal and the carrier wave, and then we pass this input voltage using this non-linear element here. So you can see that we can pass it through this non-linear element to get the output. So mathematically, if you see, you would see that this V in is passed through this output. So you can simply substitute this xt plus cos omega ct. First term is linear, it is very convenient term because this is directly V in, but second term is V in square, which will become xt plus cos omega ct whole squared. So you have to expand it by a plus b whole square formula, the standard mathematical formula. So if we simplify that expression, you would see that the output voltage would be given by this expression, this entire term here, which contains a number of terms or number of different signals. So this output is actually a combination of this entire signals which involves xt. See the first term. The first term here is actually the xt. The second term here is actually x square t, which is the square of the message signal. Third term is actually the cos square omega ct. Cos square is actually it involves the square of the carrier wave, and this last term is actually dependent on cos omega ct, which is the carrier wave. Okay, so you can easily see that this is not in the form of AM signal. This is not the AM signal. It is actually combination of variety of different things. So we are at this stage of output signal, which the output that you get from this non-linear system V out, which is illustrated here. So the output that you get at this non-linear element is actually represented by these four different terms which are shown here, and they are actually a combination, a complex signal which is not the AM signal. So the next step is to extract the AM signal out of this form. So you can see that how do we get the AM signal here. So let me quickly go back to the basic form of AM signal. In AM signal, we need to have this constant term AC cos omega ct, or one you can, if you take it as common, and second you need the product of xt and cos omega ct. If you compare this thing, the output here, the last term, this is actually of the form of the AM signal. You can see that it contains this carrier wave, which is cos omega ct. The output amplitude is also mentioned, A1. So if we compare with the standard form of AM signal, so A1 is actually equal to the carrier amplitude, which is AC, and we have this xt multiplied by 2A2 upon A1. So in standard AM form, this xt should be multiplied by mu. So in that case, if we can directly see that this mu is actually equal to 2a2 upon a1. So this is actually representing the mu. So you can see that this last term is actually representing the AM signal. The standard AM signal is represented here, where you have AC, which is the carrier amplitude, which is represented by this constant A1, whereas the modulation index is represented by this term mu 2A2 upon A1. Okay, so in order to get the AM signal from this non-linear circuit, we need to use some filtering so that we get only this last term, and we do not need these terms here which are shown by this oval. So we want to remove these terms, and we want to get the only last term. So how can we do that? So can we remove those terms by filtering or not? So this is our question, whether we can perform filtering to remove those terms or not. So let me quickly discuss each term separately. The first term is xt, which is actually the message signal. xt is actually representing the message signal. So if you look at the frequency domain view, so its spectrum would be same as the message signal spectrum. So this term would have spectrum that would be exactly same as that of the message signal. So if I draw the spectrum here, so this is the spectrum here. You can see that this first term is A1XF. This curve is A1XF, which is actually representing the spectrum of the message signal. So first is this term. Second term, if you see that this is x square t. X square t in time domain, x square t means xt multiplied by xt. So you are multiplying xt with the same signal xt. But in frequency domain, the multiplication becomes convolution. We know the standard property of transforms, that if we make a transform from time domain to frequency domain, in that case this x square t would become a simple multiplication. Would become convolution. So that means in frequency domain we are convolving this xf with the xf. So second signal would be this convolution of xf with the xf. And although convolution is not our topic, but I quickly want to point out that when we convolve the signal with xf, so spectrum would become double. I mean, if we convolve a signal with itself, so you would get a double of the spectrum. So initially for the signal the spectrum width was up to w, but when you convolve it with the signal itself, the spectral width will become 2w. So the overall bandwidth is now 2w for this xf convolution with xf. So you can see that the first two terms, they are actually dependent on the signal, and they are occupying this frequency band of up to 2w, which is the band double of the bandwidth of the message signal. Okay, let me take a look at the third term, which is this term a2 cos square omega ct. This a2 cos square omega ct is actually mathematically can be represented by, we know that cos square theta is equal to 1 plus cos 2 theta upon 2. So cos square theta actually represent a term at cos 2 theta. So omega ct, cos square omega ct is actually corresponding to a term which is actually at double of the carrier frequency. So you would see a component at a double of carrier frequency, or 2 omega c. You can see that it is represented here. So this this impulse here is actually because of this cos square term. Here you can see this cos square term, it will produce a component which is at very high frequency. 2fc is actually a very high frequency, which is at double of the carrier frequency. Okay, now we are left with the third term. You can see that the third term is this one, which is actually the AM signal. As I mentioned previously, that this has the same form as of an standard AM wave. So it will have the same spectrum as of the AM signal. So you can see that this has the same spectrum, which has a carrier component, which is shown here. Which has the carrier component, which is shown here. Similarly, it has a upper sideband, which is shown here, and it has a lower sideband, which is shown here. So this entire part is actually a carrier, an AM spectrum of the AM signal. So coming back to this discussion, I said that by using this non-linear element, actually we get this entire part, which is comprising of many different terms, and I tried to plot the spectrum of these individual components. Now what you should notice is that this spectrum can be divided into three parts. First is this part, which is actually a low frequency part, where you have a spectrum of the message and the convolution of the message with itself. It has a very high frequency part, which is actually 2 times the carrier frequency, which is representing a sinusoidal function, and it has an intermediate part, which is actually representing the AM signal, which is represented by this square block here. In order to get the AM signal at the output, what we need to do, we need to perform filtering. So what we need to do, we need to extract this part only. So we need to remove this lower frequency part, we need to remove this high frequency part. So this type of filtering requires a band pass filtering. As we have previously discussed, that band pass filter, it allows extraction of a specific band of frequencies, and now we are interested in extracting this band starting from fc minus w to fc plus w. So this entire signal is actually extracted. This entire signal will be extracted by using a band pass filtering here. So coming back to the block diagram, you can see this is the block diagram here. So the output signal need to be passed through a filter, and this filter should be a band pass filter, as I showed through this spectral diagram. You can see this spectral diagram here. So by spectral diagram, we can see that we need to have a band pass filter so that we can extract this part, which is actually representing the AM wave. So after passing it through this band pass filtering, the whatever output will be getting would be actually an AM signal. So the output will be AM wave. Okay. So this non-linear element actually generates a number of terms, but the good thing is that different terms, they have spectral components which are actually non-overlapping. Why they are non-overlapping? Because carrier frequency is generally much greater than 3W. The basic mathematical restriction is that fc should be greater than 3W. 3W is the bandwidth of the message signal. So in order to have a proper filtering to get the AM signal, we need to have the carrier frequency which should be greater than 3W, which is commonly the case. As I have previously discussed, that the carrier frequency is generally much greater than the message signal frequency and bandwidth. So So because this condition is normally satisfied, so we can easily extract this signal from by using this band pass filtering, and after the band pass filtering whatever we will get would be this AM wave. So so this is how we calculate the AM wave, how we generate the AM wave by using a nonlinear element. The physical realization that of this non-linear circuit is shown in this figure P. This is FET based circuit. So the first part is actually this. This first part is representing that non-linear element. You can see that this xt and cos omega ct are here. By using this transformer, we actually add up these two signals, cos omega ct and xt. The first step is the addition here, which is shown here. So this transformer performs the addition operation, and eventually this FET is actually having the response which is shown by this expression here. This non-linear square law based response is achieved by using this FET circuitry. And then the filtering is actually RLC filter. This is the RLC band pass filter. You need to tune it by choosing the appropriate values of the inductor and capacitor to get the overall AM signal. So this part performs the function of filtering. So after filtering you will be getting the AM signal at the output. So this is how we can get the square law based AM signal by using this non-linear element. So we will conclude the discussion on this type of circuit here. So we will be continuing this topic in next lecture inshallah. So thank you all.